as we look ahead, no, let's not look ahead. Let's look behind. All right. We learned last time about the mole. What can you tell me about the mole? Anything about the mole? Yes.
It's Avogadro's number 6.022 times 10 to the 23.
It is a number of things. Simple as that. It's a number of things. It's a very large number of things. Okay? The reason is, for us to actually even see any tiny molecules, we have to have a very large number of them together to see them. Now, we'll understand why Avogadro came up with that number later. It will come when we look at gas laws, where he derived that. But the more moles you have, the more stuff you have. Okay? And so when we write equations, we're going to relate the equation such that one molecule reacts with one molecule to produce one molecule. Okay, that's one way to look at it. But we can't see it that small, and so what we're going to do is we're going to say, okay, 1 mole of this material will react with 1 mole of this material, which reacts to produce 1 mole of this material. We could have used any number. We could have said dozens. 1 dozen reacts with 2 dozen to make 3 dozen. Okay, but what we're going to do is we're just going to use the term mole. Now, we can't count out that number, 6.022 times 10 to the 23rd things. So what do we do instead? What is our physical way that we can measure out a mole? And it was a conversion factor that is new to us. 2 names for it. Can be either MM or FW. What do those terminologies mean to you? Molar mass or formula weight. Okay? And that is given in what units? Grams for every mole. So 1 mole of material will weigh some sort of grams. Where do I get the number from grams, though? It would be, where do you actually, how do I know what the number will be? Someone's pointing somewhere. From the what? The atomic weights of the compound that you're given. So by chance, if I wanted to know the formula weight or the molecular mass of carbon dioxide, okay, how many grams would it take to get 1 mole of that? Carbon weighs 12. Oxygen weighs 16 times 2 equals 32. Add them all up. It would be 44 grams on the balance will be equal to 1 mole. Okay. Now, when we do problems, we do want to go to the hundredths decimal place, but this was quick and easy to calculate. Okay. This is a conversion factor. It will be used. Now, I may have a test question about, and I give a compound, and I'll ask, what is the molecular weight? Okay, that's a very simple question I can give. But more often than not, I'm going to use this as a conversion factor to solve another problem. Okay? And so molecular weight, formula weight is an important concept that we are looking at. Again, homework should be able to complete all the balancing by today. If you've left it to now and you're thinking about doing it in the afternoon, good luck, because concentration will diminish as the break gets closer. Okay? And as you probably can guess. All right, I'm going to teach you a couple other types of problems, and here is a type of problem. Percent mass. Okay? And here is how we do that. We take the weight of each of the atoms, okay, and you can calculate that. Number of atoms times its atomic weight, divided by the entire formula weight or molecular mass. And to get a percentage, you multiply it by 100. So the percentage of carbon in this compound, if you take 12 times the 12 carbons times 12.01 grams, that would be the weight of just carbon. This is the weight of the whole, and you multiply it by 100 and you get 42%. If I would do, alternatively, the weight of hydrogen. How many hydrogens are there in that compound? There are 22, right? And hydrogen weighs 1.01 gram per mole. And the total weight is this. Then we get 22 times 1.01, 22.22 over 342.34 times 100, 6.49%. So there are more hydrogens there, no, numerically. That's the largest number of atoms, but they weigh the least, and so they contribute the least to the percentage. Okay? And so we can ask you to calculate the percentage of any one of the atoms inside one compound. Does that seem too hard? No? Put 3 of these on the exam. You'll get, this is easy. I can do that. Okay? And mass percent. If you take a look at your CHEM-111 assignment, calculate the mass percent. Calculate the mass percent. I got 2 problems. Ooh, what's the complication that I give you in these problems versus the example that I gave you? I didn't give you what? The formula. I didn't actually give you the molecular weight. I actually make you make the compound from the ions. Oh, that ion sheet comes back to haunt us. Okay, then you calculate the formula weight, and then you have to calculate the weight of each of the atoms that is represented there. And I only asked for 1. All right, so practice on previous material. Okay, got that? All right, next concept. Oops, calculating the empirical formula. Now the empirical formula, okay, this is really easy in that the empirical formula is the smallest whole number ratio. So if I gave you a molecular formula that said C4H8, the empirical formula is reduce it. Divide each of those subscripts by 4, we've got CH2. Okay, that's an empirical formula. Now, do you think I'm going to give you problems like that? No, that's too easy. We're going to do this in terms of, we're going to do some experimental data to get this. Now, here's the reason why. When I synthesized a new compound in the organic synthesis lab when I was in graduate school, all right, I thought I made something. I believed that I made a new compound, but what I needed to do was actually calculate its empirical formula. Okay, I needed to do the work to actually get this type of empirical formula done. And so that is a proof or a support that what I synthesized, what I said I synthesized, is what I actually synthesized. So this is why we use this kind of data, is to verify something that we've actually made. But I'm going to show you how we would do that in a very simple way. And so, to calculate the empirical formula from experimental data, okay, you have to be given this, either the masses of each of the elements there, or the percentage of each element that is represented in the compound. So if the compound has 2 elements, you've got to know their masses, or you have to know their percentages. If there's 3, you have to know each one. Okay, this is what we do first. We change the percentage to grams. The reason why we do this is we assume, and this is really easy math, if I had 100 grams of it and I had 10% one and 90% of the other, well, that's 10 grams of one and 90 grams of the other. It's math without really having to do math. That's why we assume we had 100 grams, because it's easy. Okay. Second, we convert each mass of every element into moles of that element. Okay? That's mathematical. All right, here comes the hard part. Right here. This is the only time you actually have to think. You have to identify the smallest number. Okay, you think that's not hard, but sometimes it's maybe the hardest part. Okay, once you found the smallest number, you take the number of moles and you divide it by the smallest number of moles represented there. If all of the numbers are whole numbers, stop. These are the subscripts of the compound. But can we have a subscript that has a decimal? Nope. If you have a decimal, then you must multiply each number by some small whole number so that it becomes a whole number. So I'll do an example like that. Okay. So here, given a whole sample contains this much mass, that is not a piece of information that you need. It was nice they gave it to you. It was confusing that it might give it to you, but that's not what you need. What you need is the element and its mass. The element and its mass. The element and its mass. Okay? I have 3 elements. 1, 2, 3. I put their grams right here. And then I go and I take the amount of grams of sodium. I go to the periodic table, look at its molecular weight. This many grams will equal 1 mole, and I get this number, I get this number, I get this number. So I get 0.0159, 0.0157, and 0.0470. Ooh, what is my next step? Which is the smallest one? Sodium, nitrogen, or oxygen? I told you this is the hardest part. Sodium, nitrogen, or oxygen. Which is the smallest number? Nitrogen, good. Okay, I'll help you out. That divided by itself, 1. That's good, right? This divided by 0.157 is what? Essentially what? 1. It'll have a little bit of a decimal, but it'll be 1.0 and then your decimal's somewhere else. What is it when you divide this? How would you find that out? You pull out your handy dandy little calculator and it becomes what? Francesca, what do you got? Yeah. 0.047 divided by 0.0157. 2.99 what? 3, which rounds to what? 3. So what that says is how many sodiums do I have? 1. How many nitrogens do I have? 1. How many oxygens do I have? Name that. Sodium nitrate. Nitrate has a what charge? -1. Sodium has a what charge? +1. Does this make sense? Yes, it does. Nope, there. Okay, here's a different one. I start off with percentages. 53% aluminum, 47% oxygen. I change that directly into grams. I assume I have 100 grams, so 53 grams, 47 grams. I will now change them into moles. Now, this slide is wrong. What is wrong with this calculation? They're upside down. If I actually multiply those two numbers together, I will get a unit of grams squared divided by mole. That's not what I want. The conversion factors are upside down. I don't know who put that in there, but do the calculation correctly where grams cancel out. Here's what comes out in the molar ratio. Okay, this is the molar, 1.964 and 2.938 moles. What is the hard part? Which is smallest and which is aluminum or oxygen? divide each by the 1.964. I get 1 and I get 1.49. If I round this, it becomes 1.5. So my compound is aluminum 1, oxygen 1.5. Yes? No. What can I multiply? What small whole number can I multiply everything by to get a whole number? If I multiply that by 2, I get 3. But if I multiply this side, I have to multiply this side to get 2. And so my whole number is 2 to 3. So I get aluminum. What? Aluminum what? What is that compound name? Aluminum oxide. Oxygen becomes a charge of -2. Oxygen becomes a charge of, oxygen becomes -2. Aluminum becomes a charge of +3, right? So crisscross 3 down, 2 down. Does that make sense? Sometimes you can check these by looking at the compound that it's made. Does that make sense? Sometimes you can make sense of them to check. Okay? And so we can calculate an empirical formula based upon data. Empirical formula, small whole number ratio. Okay? Now, if I give you one more piece of data, you could take an empirical formula and go up to a molecular formula. Okay? You have to be given the empirical formula, or you now know how to calculate it from data. So it could be a long problem. You also have to have the formula weight or the molar mass of the entire compound. This is what you do. You calculate an empirical weight, the weight of the empirical formula. An example of that, this weight right here of the empirical formula would be 12 plus 2 more, 14 grams per mole. Okay. And you have to have the formula, the molecular formula of the whole compound. The molecular formula of that whole compound is what? Carbon equals 4 times 12 equals 48. Hydrogen equals 8 times 1 equals 8. 48 plus 8 is 56 grams per mole. Okay, now check this out. 56 grams per mole. That's the weight of this. 14 grams per mole. That's the weight of this. If you divide this number into that number, what do you get? 4. That's a small whole number. If I take this 4 and multiply it by, what number is understood there? 1. Take 1 times 4, I get 4. And if I take this 4 and I multiply it by that number, 4 times 2 is 8. So what you're going to be given is this number here as a given entity. And you're going to be given at least this or data to get this, because you just learned how to do that, so that I can get this one. If you take the molecular weight, the whole weight of the entire compound divided by the weight of its empirical formula, you're going to get a small whole number that can be used to multiply against the subscripts of the empirical formula to get to the molecular formula. An example here, this compound here has 88 grams per mole. The whole compound is 176 grams per mole. I get a number of 2. So what I do is I take C3H4O3 times a 2, and the molecular formula is C6H8O6. Okay? All right, so let's take a look. Oh, number 3. calculate an empirical formula. Number 4, calculate an empirical formula. Now, number 5, calculate an empirical formula. Ooh, number 6. There's an empirical formula, an empirical mass, and a molecular formula. Ooh, that's that whole problem. That's the next step. And so now we can do homework 1 through 6. All right. Stop. Okay. This is the big concept that we're trying to get to, though, is something called stoichiometry. What we're going to do is we're going to derive relationships from the balanced equation. The reason why we looked at balanced equations is we're going to relate things. Okay? We're going to relate the reaction of one thing to the next. And really, this is what we need to know. Let's say I was tasked to do this. My job is to make 100 grams of a product. Okay? And that's my whole job today. And I get paid if I make 100 grams, or I don't get paid. Okay? And I know the reaction. And so I have to go to the stockroom, and I have to go in and find out, well, how much material do I need to start with to produce the 100 grams of material that I want to produce at the end of the day. The only way that I can do that is if I knew what the reaction was and what the ratios will be between the starting stuff and the ending stuff. And so the equation is very important for us to understand what's going on. And so in terms of complexity, this is probably as complex a calculation that you would have done in high school. And so the question is, how many grams of water are produced from burning 1 gram of C6H12O6? Okay, that is the sugar glucose, and we are going to add oxygen to it. And if I take glucose and add oxygen, classify what kind of reaction that is. It is combustion of a hydrocarbon. You could have predicted that it would have made CO2 and water. So the first thing you have to do is predict the products. In this case, I gave it to you. Second, it is meaningless unless it is balanced. Okay, and that is by adding a 6 in front of the oxygen, a 6 in front of the CO2, and a 6 in front of the water to balance this all out. Third, calculate what you're asked for. Now, here, this first step, calculate grams into moles, okay, using the molecular mass. Stop. Here's the molecular mass, okay? It is being used as a conversion factor, all right? For us to relate things in a balanced equation, we have to get to moles. Now, here is the key to the whole situation. If I want to relate two things in an equation, I do this. I identify what two things I want to relate. This into this. And so there is a relationship. For every 1 mole of the glucose, I'm going to produce 6 moles of the water. You take a ratio from the balanced equation. This number, coefficient 1, goes to 6 of those. That's the key to being able to transition from one thing to another in a balanced equation. And so I've gone from something A to something B. And in this case, water. Now I go back up here. It says how many. It didn't say moles of water. It wanted grams. So I can again use the molar mass to get from moles to grams, and we can calculate the value. Okay? And so, in this case, the new entity, the big piece of the puzzle, is using this. The other two conversions were something that you already knew how to do. We're just putting them together. All right, let's try one of these things. And let you see how it looks. All right. Oh, 7 is complex. There's a little bit more to 7 and 8 and 9 and 10 than you probably want to know. All right, let's see if 11 works. Oh yeah, okay, here it is. This is the biggie. All right, what in the world are we going to do? Ammonia reacts with phosphoric acid to produce ammonium hydrogen phosphate. All right, that was the biggie thing at the top there. Ammonia reacts with phosphoric acid to produce ammonium hydrogen phosphate. Boom. All right. If 10 grams of ammonia reacts, how many moles of ammonium phosphate fertilizer will be produced? Okay. Other than crying in the corner, what do we do? What would the first step that we need to do in this to solve this problem? We need an equation, right? Okay. Well, I'll be helpful. Right? What does it react with? Okay, phosphoric acid. Uh-oh. What is phosphoric acid? Okay, we start with H. Good, good, good. Okay, PO4 is in it, yes. What charge is a PO4? A minus what? This is a minus 3. So how many hydrogens do I have to have? 3. Okay, ooh, naming. So those are the two things that react. Oh, what was good was they told you exactly what it's going to end up as being. NH4, 2 of those, H, PO4. Okay. All right. Well, goody. Am I done? No, I just have the reactants and the products, but I haven't balanced it. What element do you want to balance first? Nitrogen. That sounds like a good one. How many are here? 1. How many are here? 2, right? And so, it went away. Okay. So how do I make this 2? Put a 2 in front of this, right? Great. All right. Phosphoruses, how many on each side? Okay. How many hydrogens on each side? How many here? 6 plus 3 is 9. How many right there? 8 plus 1 is 9. Good. And oxygens? 4 and 4. Okay, I got a balanced equation. I can now start doing things. All right. Where do I start and where do I go? Okay. If I look at this, and what I want to show you is how to use the map. Where is the beginning of this? Do you know? If I want to do this reaction, or I want to do this calculation, what's the first thing I start with? 10 grams of what? Ammonia. Okay, so 10 grams of A. All right, here's the big map. I've got moles of A and moles of B. A in my particular case right now is grams of ammonia. Where do I want to go at the end? Moles of ammonium hydrogen phosphate. All right, where is that? That's moles of B. Can I go from grams directly into moles of B, grams of A to moles of B? Where can I go next? What's the direct relationship? I convert grams of A into what? Moles of A. And then once I have moles of A, I can go to moles of B. What this tells me is I have 2 multiplication steps to get where I want to go. The multiplication steps have grams of ammonia to moles of ammonia, and then moles of ammonia to moles of this thing. Okay. All right, so next. Okay, I got this. Well, that's all good. Well and good. All right, where do I get my numbers? How do I get the molar mass for this? Periodic table. But for CHEM-111, you've got to go to its periodic table. Okay. Nitrogen, hydrogen, and I hope I'm going to select a 3. Okay. So 17.031. Nope. Is that correct? No. I messed up. I did my calculations correctly. 1 mole is 17.031. Okay. So 17.031, and that is a what? All right. Where do I get my next set of numbers? Where do I make a relationship between ammonia and the ammonium hydrogen phosphate balanced equation? What number goes here? 2. What number goes here? 1. Okay. All right. Someone do it for me. What's the number? So many calculators, not a lot of movement. What we get? Okay, go ahead. 0.293 what? 58. And that's moles of the thing. Okay, so how many sig figs? 4. 2.936 e to the minus 1, or it would accept 2936. I think that's easier for me. So 0.2936. Say that again.
The second drop in version.
Oh, that is a good thing. Oh, I would have had a big red box. Okay. Yes, yes, yes. Okay. All right. Every time you feel just a little bit before you hit the submit. And good. I've earned points. All right. In this, stepwise. First, predict what's going on. Sometimes that means you just interpret what's given. We had to make this compound correctly. That was given. This was given. If you didn't make this compound correctly, balancing would be really, really hard. Okay? The second is to balance it. Then we identify where we start, where we're heading to, and then we have to put in enough conversion factors to get from one place to the other. This was the key new conversion factor, using the balanced equation to derive a relationship. Now, There's another one that you saw yesterday. Okay. In relationships. Okay. In terms of 1 mole of this compound, how many moles of aluminum are there? If you had a whole mole of this compound, how many moles of just aluminum do you have? You actually have 2. Okay? There's a relationship that you can take from a balanced equation. There's also a relationship that you can take from the compound itself. And we saw that in that problem yesterday, the last problem that we looked at, that there were 2 moles of aluminum for every 1 mole of the whole compound. If I took it apart,